In summer, this freight train can stretch more than 2 miles. At -45, the rulebook can cut it to less than 1. Nothing broke, only the temperature changed. Every winter, freight trains across the coldest parts of North America lose length on purpose. Under Canadian National's coldest tier, a bulk or intermodal train supplied with air only from the lead locomotive can be limited to 4,500 feet, down from a warm weather ceiling of 12,000. The limit is not the diesel engine. It is one airline, running from the first car to the last. This is the story of that pipe, how it controls every brake, why deep cold pushes it to its limit, and how engineers win the lost length back. Look under the train. Running beneath every car, from the locomotive to the very last coupler, there is one continuous pipe, the brake pipe. The locomotive's compressor keeps it filled with compressed air, typically charged to around 90 pounds per square inch at the head end. That pipe solves an old and brutal problem. A freight train can run 100 cars or more, and in the early days of railroading, there was no way to brake them all at once. Brakemen worked on the roofs of moving cars, setting handbrakes wheel by wheel. George Westinghouse replaced all of that with air. And here is the part most people get backwards. That air does not stop the train. It keeps the brakes released. Each car stores compressed air in its own reservoir. The brake pipe charges that reservoir and carries the command. When pressure in the pipe falls, a valve on each car sends air from its reservoir into the brake cylinder. So the locomotive does not push braking air through 2 miles of pipe to every wheel. The energy is already waiting on each car. The pipe tells it when to act. To slow down, the engineer lets a measured amount of air out, and along the whole train, brake shoes press against wheels. The braking force happens at the wheels. The command coordinating every car travels through air. If the train ever breaks apart and the pipe tears open, every car brakes itself, automatically. That failsafe has been the standard for about a century and a half, and it still controls the heaviest trains on the continent. One more detail. The pressure change is fast, but not instant, roughly 700 feet per second. On a 12,000-foot train, the command reaches the last car about 17 seconds after it leaves the first, and building the full braking force takes longer still. A brilliant system, until winter tests it. So, what does extreme cold do to that pipe? It attacks the joints. Between every pair of cars, the pipe connects through flexible rubber hoses. Inside every car, valves, gaskets, seals. Canadian safety investigators describe the effect in one sentence. Rubber seals and gaskets become stiff, metal contracts, and pressurized air starts leaking out. Stand next to a parked freight train on a brutally cold night, and you can sometimes hear it, a thin hiss of air escaping at the connections. Moisture makes it worse. Any water in the air can freeze inside valves and fittings, which is why modern locomotives dry the air before it enters the pipe. No single leak is dramatic, but a freight car is not one machine, it is a link in a chain. Every car adds valves, seals, hoses, and connections, potential leakage points repeated along the entire train. 100 cars, 200 cars. Below roughly -25 Celsius, the losses climb sharply. Now the compressor at the front is feeding a pipe that never stops leaking. The longer the train, the more airflow it takes to hold the line at pressure, and the bigger the pressure difference between the locomotive and the last car. Railroaders call it the gradient. The head of the train sits at full strength. The tail charges slowly, and, just as important, it is slow to fully release its brakes. The crew can compare both ends. A gauge shows pressure at the locomotive, while the small flashing end-of-train device on the very last car transmits rear pressure to a receiver in the cab. And the rules put a hard number on it. Before departure, American regulations require at least 75 pounds per square inch at the last car, within 15 of what the train is set to run at. If rear pressure cannot reach the required threshold, a sufficiently long train can fail its departure brake test. The air brake system becomes the limiting factor on the whole train, so the railroads did the math. Here is that winter guide in full. Canadian National publishes it as an actual table, and it reads like a staircase going down into the cold. Start with the conventional layout. The lead locomotive is the train's only air source. Take a bulk or intermodal train, grain, coal, or containers. In warm weather, trains like this run up to about 12,000 feet. Below -25 Celsius, 8,000 feet. A third of the length, gone. Below -31, 6,000. Below -36, which includes a night at -45, 4,500. From more than 2 miles to less than 1. Not because anything broke, because a row in a table said so. This is not a recommendation, it is an operating instruction. The forecast moves the train into a colder tier, so its permitted length is reduced before departure. The logic is simple. Cold increases leakage throughout the train. The longer the brake pipe, the more airflow is required, and the larger the pressure difference between the locomotive and the rear. Eventually, one air source is no longer enough to keep both within operating limits. So the railroads shorten the train, or add air sources. And this is not just Canada. In the United States, BNSF runs the same playbook. In an advisory from February 2025, the railroad put it plainly. With the Arctic cold, additional locomotives are required to generate proper airflow for the train's braking systems. And train lengths are restricted until conditions improve. Different country, different company, same physics. Cold hits the rest of the railroad too. Fuel thickens, steel turns brittle, switches freeze beside their heaters. But the length problem is the one with an elegant fix. Remember the phrase, shorten the train or add air sources. The problem was never the cold alone, it was geometry. One compressor at the head, feeding a leaking pipe that stretches for miles. Every extra foot of train is another foot of pipe, more joints that can leak, more distance for the pressure to fade across. Why not simply use a bigger compressor? More compressor capacity can supply more air, but the brake pipe still operates at a set pressure. One source at the head cannot eliminate the gradient created by miles of distributed leakage. The rear still has to reach its required pressure. So railroads shorten the train, or place additional air sources farther back. Railroads can add air in 2 ways. One is distributed power, locomotives placed inside the train and controlled from the lead cab. The other is an air repeater unit, a dedicated car or container carrying compressor and control equipment instead of freight. If you have ever waited at a crossing and watched a locomotive rumble past in the middle of the train, not pulling at the front, this is one of the things it was doing there. CN's winter table has a code for the classic layout: 1, 1, 0. One air source at the head, 1 in the middle, 0 at the tail. That second source does not split the pipe in 2. It is still one continuous line. It places a source closer to the rear, cutting down the maximum distance air has to travel to reach the farthest car. Shorter distance, smaller gradient, a tail that charges properly and releases properly. In CN's coldest tier, a bulk or intermodal train with a single air source is limited to 4,500 feet. Add a second source, the 1, 1, 0 layout, and the limit rises to 6,700. Each additional source beyond that configuration buys another 2,000 feet, up to 5 sources in the whole train, and the ceiling comes back 12,000 feet. The full summer length, at -45. Other freight categories use different numbers, but the principle is exactly the same. So, when a crossing gate drops somewhere far north this winter, and the train rolls past shorter than it was in July, nothing is wrong with it. Someone read the temperature and counted the air. A century and a half of engineering, and the answer to the deepest cold is not a stronger engine or thicker steel. It is where you put the air. Somehow, it works. If you enjoyed this, watch what happens after a cargo ship stops its main engine, and why the machinery around it keeps running.